Hi, my name is Keith Rayle, and today we're going to be talking about artificial intelligence. And the purpose today is to give you some kind of a foundational knowledge or at least a basis for understanding the technology and how it works. A little bit about my background. I spent 21 years in the military. I started off in the United States Air Force playing around with nuclear weapons and things. I was a nuclear weapons technician. And then I went over to the Army. I was a test pilot, threat officer, had various leadership roles. I went to flight school, and I flew just about every helicopter they had. And since then, I retired out in 1997. And since then, I've been in security management consulting, doing a lot of different things out in the IT security world. Some of the places I've been to includes NASA JPL, the World Bank, the Chicago Mercantile Exchange, Delta Airlines, Humana, Hawaii Electric Company, Honda North America, USA, Corning, and many others. I've been a consultant, a practice manager, a director of security, and a CISO. So I've got a fairly wide range of experience behind me. Currently, I'm an IT and security strategist. I work at Fortinet, and my approach to security and how we do our jobs as security professionals, how is it that we can be successful in what we do? And I look at it like in this perspective, we have resources that are fairly critical to us as far as the technical, highly skilled technical resources. And we have technologies out there. If we take technologies and leverage that into our organization, we can take those resources and use them where we really need them. And when we do these two things and we marry these up to the business needs, this is where we become successful. So, one of the issues right now with artificial intelligence is the fact that it's become almost a buzzword bingo type of a term. We used to play this game a few years ago, and basically how it worked was we would take a bingo card going into conference presentations and things like that, and it'd have the latest buzzwords that marketers and people were all yammering about, and they didn't make much sense really. They didn't tell you much, but they were the buzzwords. And here you can see e-business and center of excellence and ramp up and heads up, due diligence, and so throughout the course of that speaker's talk, they would start yammering on these buzzwords. And you'd cross that off on your card. And the first one that got bingo, any 5 in a row would jump up and yell bingo. And of course, everybody else that was playing would groan and tear their cards up, and the speaker wouldn't know what was going on. And to some degree, that still goes on today. We have all of these buzzwords that hit our talks, presentations, and when people try to sell us things, they come in the door and they'll hit these terms. Right now, the ones that are popular include deep analytics, crowd culture, virtual and augmented reality, and we always hear about big, real big, way, way, way big data, and holistic fill in the eco fill in the blank. But three terms that get bandied around a lot without much explanation as far as what's really being done with it or what it really means are these three terms: artificial intelligence, machine learning, and deep learning. Now, in relation to today's talk, I want to focus on how AI can be used for antivirus and virus management. And so the current challenge is that we've got two approaches that we use, basically, to managing malware. The first one came about in the earliest days of malware, and what we did was we captured a sample, and we would run an MD5 or a SHA-56 one-way hash of a file, and then we would store that in a pile off on the side. And if another file came in and it was suspicious, or we would maybe do this with all files or attachments, we would run that file through the same hash that we used, whatever it was. The MD5 or SHA typically, and we would end up with a single hash value. And we'd go over to that pile of hashes that we had, and we would do the comparison and see if it was in the pile. If it existed in that pile of known malware, if the hash matched, then we knew that we had malware and we could throw it out. So it was a one signature, if you will, was related to one piece of malware as it came in. Now, the bad thing about it is this was very reactive and non-responsive to mutations. In other words, we kind of had to be hit sometimes to even be able to capture the sample. And if somebody changed anything in that file whatsoever, it would change that signature or that hash value, the ID of that file coming in. So you couldn't deal with mutations of software very well. So the next phase, or this next kind of a level of antivirus management, kind of looks like this. We have content now. Let's go ahead and pop these things apart in a sandbox, possibly run them in emulator mode. But we basically extract information within those files. We look for patterns and how these code blocks within these files relate to malicious behavior. So we even look at the wrappers and the payloads separately. So the wrapper is typically, think of like WinZip or something like that, or something that compresses a file or whatever. We have this wrapper that comes in. Now, some malware is wrapped inside of things like Word documents and PDFs and things like that. And just by virtue of the fact that we open it or we enable macros, we can be hit with whatever content is in this file. But we look at wrappers and that malicious payload for repeats of code pretty much. And we create these super signatures of these code blocks using them. Now, the nice thing about it is that it'll handle it, this approach can manage large volumes of permutations with a single signature. For instance, when WannaCry came out, you rapidly saw it being changed into other types of malware. The initial strike was ransomware. And within 24 hours or so, we saw botnets, we saw cryptocurrency miners and things like that. So it went from being ransomware into being something completely different because they changed the payload and behavior and the characteristics within certain code blocks. So anyways, when we take this approach and we look at the code blocks versus just the whole file, and we create these super signatures, if you will, we can be very, very proactive in nature. In fact, you can even catch zero-day attacks using this method because most zero-day attacks don't really use brand new code. What they're doing is they're using a brand new vulnerability within an application or hardware. For instance, the Apache struts attack that was successfully launched at Equifax. It was that single vulnerability. The code that was used wasn't necessarily new. So again, this is kind of what we're going to use as the basis for our talk about AI. But now let's think about those code blocks and malicious behavior as we explore what AI is. Let's start back with the history of it. So our goal for today is to basically be able to show you this representation of an AI system and you understand what the bits and pieces are and what's really going on here with the files as they fly into the system. What's going on with that feature set? How is it resolving into a determination if something's malicious or clean? But let's start back with the history of AI. Basically, Alan Turing, he was a brilliant, brilliant individual, broke the Enigma machine that resulted in radically shifting the power in World War II. And basically back in the early 1930s, he looked at an infant's mind like it was an unorganized machine. He created these early definitions of machine learning by visualizing logic gates, negative AND gates. And then there was a modifier of it that added in weighted, that resulted in a weighted input and a variable output. But apart from how the thing would work on a mechanical level, his brilliance came in from these three basic bullets that you see up here. He knew that you'd need a seeded solution set of accurate or known potential output. So in other words, if you were to put something in, you would get an expected output. He also knew that in order to have a machine that could think, you'd need a population of variably weighted pieces or functions without it. Some things would have to be more important than others. He also knew that you would have to have a method of removing the worst solutions while retaining the very best. The thing that really inhibited his research was he was far ahead of his time as far as his thinking versus what could be actually created in terms of the computers of that day. So, from a historical timeline, we look, and off to the left, in the later 1930s, he teamed up with Klein and Church, and he proposed a machine learning solution. And it wasn't actually proven until 1943. So again, he was well ahead of his time when a formal design, a very simplistic design, could be created. In 1956, AI was formally founded as a research discipline at Dartmouth College. In the 1960s, most AI projects were heavily funded by the United States military. Now, the British government was also starting to invest heavily in it. But the first AI winner, if you will, or basically AI became, it kind of halted in its growth in 1974. And basically what happened was the dollar was decoupled from the gold standard, and there was a general global economic upheaval at that time. Even within the United States, we saw the government step in and apply pricing controls to gasoline and bread and things like that. And so the money that was being used for AI research was pulled from that in order to fund social programs to help populations through these difficult economic times. And then the funding started coming back in again, some of it from the private sector. Commercial companies were starting to invest in it, and then it hit somewhat of a second winter. And what happened was in the 1980s, Lisp was created as a program, as a programming language. I believe it was at Bell Labs. I'll have to look that up to make sure, but anyways, Lisp was created, and it was the language of AI, and it was allowing people to start building constructs in AI and things, and companies were investing in it until the PC came along. IBM created the desktop PC, and the next thing you know, companies are ignoring AI because they can get these desktop PCs with these amazing things like spreadsheets and pie charts, and all of their business solutions could be solved by these desktop PCs. After that, AI again started to take off, and we saw it being applied basically at data mining, medical diagnosis, etc., as CPU power was increased through the 1990s. In 1997, the Grand Master Kasparov, the Russian, was beat by the IBM Deep Blue AI system. And as a child, I remember watching Bobby Fischer and Kasparov play their world chess championships and things. And so, anyways, we kind of kept going with with increases in AI and deep learning up through the 2000s. Watson defeated the Jeopardy champions and things like that. And then all of a sudden, here we are, 2015. There were 2,700 plus AI projects in place at Google alone. In 2017, Elon Musk called for the regulation of AI before we hit that 100-year mark. Shortly after that, Vladimir Putin said, whoever rules AI is going to rule the world. And so that's where we're at today. But it's the main point of this slide is that AI is reaching nearly a century old. Now, how does AI work? What are we trying to do with AI? And basically what we do when we create these systems is we're trying to get them to solve problems much in the way that we as human beings solve them. And there's two approaches that we take as humans to sort through our environment, learn about it, and react appropriately. The first is a supervised learning approach. Now, what happens here is it's the reinforcement model, and we understand this from our days in school. We would learn a certain amount of information. We would get tested to make sure that we learned it. And if we did well on the test, we got our gold star. If not, we had to possibly retake the test over or drag a bad grade home to our mothers and fathers. But it was the carrot and stick approach of learning. Then there's the unsupervised learning, where we take these unknown solution sets and try to make sense out of them. And we do this according to a couple of different approaches. The first one is that we cluster things in our environment according to similarities to determine what's going on. Another approach we use is dimensionality reduction, which is the deductive reasoning. If A and B, then C must be true. We use structured prediction, where we look at random fields and we analyze them to predict according to our defined output of probabilities. When we drive down the freeway, we use structured prediction. We see how fast traffic's moving. We see where the slots in traffic are, how fast or how far behind the next car we are, how far the car behind us is from us, who's coming along very, very fast and weaving through traffic, or who's slowing things down. And we adjust our drive according to our structured prediction of what that situation is going to look like in a few seconds or a minute. And then we use anomaly detection. And I like to say this is the Where's Waldo of the human experience in trying to solve problems. But often we look at anomaly detection also as an input does not match expectations. What does that mean? I did this and this did not happen. What does that tell me? And so in order to solve problems, we've created things called artificial neural networks. And these are large collections of simple interconnected nodes or neurons, and each has this weighted input and output decision capability, or an output value that it provides. And also one more thing, the problem solving that we're going to focus on for this particular AI analysis is going to be a supervised learning system. And we'll get into how that works in just a minute. Now, let's talk about this artificial neural network, if you will, or a multi-layer perceptron. An artificial neural network consists of 3 or more layers. And there are 3 terms here that I want you to come out with today when we talk about artificial intelligence. The first term is layer. A layer is a piece of the system that has a general responsibility, if you will, to solve a particular problem. Now, the layers in an artificial neural network, there are some that we can see and there are some that we don't see. We don't know exactly what's going on in there. The ones that we can see are the input layer, where we feed data in, and the output layer, where we receive something back. But inside those hidden layers, we're not really quite sure exactly what's going on, but we can infer what happened based off of what we fed in and what we received out. Now, the second term I want you to think about is a node. Layers are made up of nodes. Now, a node is nothing more than a small application that does a discrete piece of processing of input information, what it's fed. The node is connected to every node in the prior and subsequent layer. And each one of these little applications or nodes finds some percentage of what it's looking for, and it produces an output based on that, what its function is and how much of what it was looking for that it found. And so it provides a weighted value, if you will, or a percentage of what it was looking for as an output, and that gets passed forward through the system. It's very, very similar to human neurons. If the input is strong enough, the signal is passed according to the weighted value. And what I mean by that is if a node finds 100% of what it's looking for, and what it's looking for is important, then that little signal that it passes forward is important to the result or the output layer. And we'll see how that works as well in a minute. Now, let's talk about machine versus malware. If we were to be able to take an AI and build a 4-layer system, we could build a system that we input a file into, and then the second layer of this, the malicious layer, maybe we could pull apart and look for things that indicate malicious files. And then we have the next layer, which we'd call a clean layer. And maybe we can teach that layer to look for non-malicious file features or pieces of code block or whatever it's looking for, if you will. And then we would have this output or decision layer. So we could actually build an AI that tries to find malicious and clean files based off of the number of nodes that are in there, typically billions of nodes, and what it's actually picking up and trying to find. And so this would be the basic construct or architecture that we're going to use moving forward in this discussion. Now, what is a feature? What's it looking for? What's going on there? A feature, when we talk about AI, and by the way, this is your third term, layers, nodes, and features. That's what makes up an AI system. So a feature, what is a feature? It's a point observable characteristic, and in our instance, it's based on code blocks. We're talking about being able to analyze clean files and malicious files to be able to determine without knowing when they come into our system if they're clean or malicious. So these files, when they fly into the system, are basically pulled apart into those code blocks. Could be detonated if it's malware, or we could even look at those wrappers and packers and how the thing is, what it takes to be able to even set off that malware. But we parse those files into code blocks when it enters our system. Now, this feature is that point observable characteristic, or that one thing that we're looking for. And in our instance, it's a code block. Now, a feature will have a one-to-one relationship with a node. And what I mean by that is you'll have a big pile of nodes, or those code blocks, if you will, that are maintained in a knowledge-based repository. A node will go out and grab a feature off of that pile based off of how it's ranked within that structure. It'll grab a feature or a code block and go look for it. That code block is not looked at by any other node in our system. That node won't go out and grab a feature and look for it, and then go grab another feature and look for it. There's only a one-to-one relationship. One feature is looked at by one node. These features are maintained in a repository, a rather large repository, and they're ranked according to their importance. Now, that ranking is what provides quality, and the quality is critical to the system. This provides a more accurate determination of file status. We leverage internal legacy samples of approximately half a petabyte to create features from the samples. This is what our company did with our AI, but each feature is weighted to assist in decisions. And what I mean by that is that as that code block gets picked up and looked at by a node, it comes in with some kind of a numerical value as far as how important it is in relation to all the other features. And I'll show you how that gets done or accomplished within the system as well. But each feature has that weight that's applied to it. And that weighting, or that numerical value of that feature, can change over time. So if we sit back and kind of think about this, we have a node that looks for something, and based off of how much it sees, it provides a numerical value. And that something that it's looking for has a numerical value as well. And so if we take these features and the persistence or the availability of them within whatever it is we're analyzing, we're basically kind of doing a big mathematical add as far as coming up into a probability, if you will. How does it work on a single instance? Now, I told you that we really don't see what's going on in these hidden layers. We don't really have a clean view, but if we look at one node, one operation, we can easily understand what's up. And here's how it works. So we have the input layer and we feed a file in. It's either malicious or clean. We're not sure what happens here, but let's take a look and see if we can determine if it's malicious or clean based off of a single node 4-layer system. We input the file in a single node per layer. So we input this file, and the first node in the malicious layer looks out or goes out and grabs a malicious feature. And let's say that there's 100 points of weight that's applied to that feature, but it only finds 90% of the congruent ones and zeros of that block code or feature. It's going to pass forward a plus 90 valuation of it. Now let's go to the next layer. And here's a clean layer. This layer only looks for clean files, non-infected stuff. And it goes out and it grabs a feature that's worth 100 points as well. But it only finds 20% of that code block, the ones and zeros, congruent within its search of that entire file. And so it's a simple add and subtract. 90% probability that that feature existed within that malicious layer analysis, and we have a 20% probability that that feature existed when it does its clean layer analysis. The output is a 70% probability as far as the result. And so when we feed a file in and we were to do this type of an operation on a very simplistic system of one node within each of these 4 layers, there's a 70% probability that we had some kind of a malicious program that tried to get into our systems. Now, the complexity comes in when you consider that each one of these nodes that are grabbing these different features are connected to every node prior and preceding within the system. So you can have billions of nodes in the malicious layer. You can have billions of nodes in the clean layer. And you have more features than you have nodes. And so you do this calculation if you think every one of these is an add subtract mathematical operation that occurs. And so the more heavily weighted features and the nodes that find that higher probability is what actually gives us that result. But this whole model is nothing more than one huge mathematical operation. So in our case, we have a 2.3 billion malicious layer node and a 3.2 billion clean layer node. And again, this is for the purposes of this discussion. If we were to think about it, that output would be reached due to the computation of 2.3 billion times 3.2 billion smaller little computations. This is how we come up with that result. Now, the layers and nodes and features, those 3 key terms that we talked about earlier, this is what provides a system with the ability to learn. So the system's fed initial data sets for analysis, and this we're going to take a supervised machine learning approach. And I'll show you how this works graphically in a second, but we break those files into code blocks. And the information or those features, those code blocks, are extracted during a learning phase. And there's binary present within those blocks, and that binary represents behavioral activation of something, whether it's a malicious or a clean file. And the system learns to weight those features based on the surety of indicators, or the tells for you poker players. Think of somebody rubbing their ear every time they have a pair of aces, you know to fold. It's a surety of that indicator. It also learns to weight the features based on how often it sees that feature come through the system. And so it changes and modifies those features over time. But basically, the approach of using a layer with a general responsibility that consists of those nodes, which are small little applications, and their only job is to pick something up and look for it. And the something they pick up is a feature. Those 3 pieces is what gives this capability, the ability to learn, or gives this system the ability to learn. Now, what happens with features, databases, and the potential performance of the system? We don't want active features to grow linearly because they're kind of laying in a pile as it is. And those weighted, the weighting that we apply to those features in that big pile, it adjusts their position in the pile. Some features, due to the fact that others may get weighted more heavily, could be completely eliminated from consideration. And there's even new features that can get created. We may not have a particular code block in a file that we feed, and so we look at that code block, or the system looks at the code block. It's something new. I'm going to put it in my pile of features. If it already exists, of course, the weighting value is changed according to what it discovered as far as the output. But anyways, these features can get eliminated from consideration. And so real efficiency within an AI system is realized when the entire feature set that you're using at that time is comprised of features that have been seen more than one time. The speed improves as the system learns to seek the more heavily weighted features. In other words, you get to a point of surety in your computations when you're picking up these features and they have the weighting. And the more important ones are signaling that, yes, this file is absolutely a clean file, or this file is absolutely a malicious file. You come to that decision faster as you get these features weighted out according to their importance in relation to each other. And so the system can come up to a decision much faster as these features become much clearer in their weighting value. Now, that doesn't mean that a single instance of a 100% feature stops the processing. It doesn't. It comes up to a probability event within the system being able to determine if a file is malicious or clean. But let's take a little bit of a look now at how does this thing really work? And here's the nuts and bolts of it. And hopefully this ties together all the concepts I've been talking about so far. All right. All right. So let's talk about how do we even start with one of these systems? How do we build one of these? And basically, we start with an empty AI system as far as its feature repository. Now, the repository, what we're going to place in there are code blocks that we get from files. I just want a little side comment that to try to build this repository manually would not only take an enormous amount of time, because we're talking about collecting up billions of code blocks, but it would also result in a system completely useless to us, because the thing that we want to avoid is a human determining the value, the weighted value of the feature sets. We want this system to kind of teach itself, but we are going to see how well it did in its performance of that task. But just due to the complexity of the problem, you cannot have a human build out this feature set. And don't forget, the feature repository is going to be filled with code blocks that indicate whether a file is malicious or clean. So we start with this AI and a completely empty feature repository. Now we're going to take and apply training files into this system. Now, they're called training files because they're tagged. We're telling the system, this is a malicious file. Oh, here's a clean file. And we feed these into the system. As we feed it into the system, it blows those files apart into the code blocks and starts dropping them down into the feature repository. And so it breaks it apart, takes the code blocks, marks them as malicious or clean, and puts them in that heap. Now, as we feed it more and more samples, we feed it another sample and we tell it, hey, this is malware. And it says, okay, this is malware. And it breaks it apart and there's the code blocks. But it looks down the repository and goes, hey, wait a minute. I've already got this feature and I know it's malware. This is more important now. And so it changes the weight value of that code block that it saw the second time. And this happens over and over. It'll see maybe a code block 100 times that indicates malicious. And each time it sees that file, it increases the numeric value of that feature. And so this is how we basically kind of train the system up. We feed it files, it breaks apart those files into code blocks. Everything's marked so it knows what it's being fed. Then it creates those malicious and clean features down in the repository. And don't forget that AI system is consisting of those 4 layers. Now, how do we know if it performed well in its weighting value and its analysis or its creation of that feature set? We're going to go ahead and give it a test. And here's the carrot and stick approach. This is supervised learning. Now we're going to test it by feeding it files, but we're going to remove those tags. Now the system does not know what it's being fed. It could be malware. It could be just a regular file, a clean file. So what it does is, using that feature repository, it analyzes. It looks. It takes the samples apart and it looks for the features to try to determine if something's malicious or clean. Now, the interesting thing is, even as we're testing it, it is still learning. My running joke here with this presentation, and I'm sorry, I'm going to say it here as well, is usually when we as humans get tested, the only thing that we learn while we sit for that test is we should have studied harder. The AI isn't like that. It's continuing to extract code blocks. It's continuing to change that weight value of the features within a repository. So it makes a determination if something's malicious or clean based off of the analysis of what came in, that breaking apart. It looks for code blocks that indicate malicious or clean, and then it says, oh, okay, well, the probability is very high that we're dealing with a malicious file because I found these code blocks within it. Or this is probably just a really safe Word document because it matched up with all of the clean features that I had down there, the clean file features. How do we know if it really learned correctly or not? We know what we fed it, these testing files that were unmarked, and we knew what the output was. And so we examine those results. If this system passes and it performed adequately, we continue the training of it, or possibly even put it into production. If we find errors in that output, what we do is we reset that whole system back to a known prior state and start again. We'll feed those training files, maybe in a different order, or maybe we'll take completely different ones and try that approach. But we continue to train it and test it, train it and test it. And this can actually take years to do based off, depending on the size of the system, etc. So what's it look like in operation? We have these raw samples that are flying in, and we've got these layers, and these layers consist of nodes, and those nodes are, the files are being popped apart, and we're looking at those code blocks, and we're in the feature set now, and we're trying to determine if they're clean or malicious. Oh wait, we have a new code block. We're going to add that to the feature set. Oh, there's a code block that we saw before. This might be important based off of our output, so let's put it on the side and increase the weight value if it's clean, if it's a clear indicator if something's malicious or clean. So this whole feature set is dynamically evolving as this system is in production or operation. We have the output, and basically at that point, we've got a system that's taking unknowns, running it through kind of like a big filtering process, looking for code blocks that it knows about. And it's repopulating features, it's changing those weights, et cetera, and giving us that output and able to predict what's going on. Now, one thing that's interesting about the system is we're not really interested in getting as many possible code blocks as we can. What we're looking for is the quality. Like I said before, the best features are or code blocks in this case, are the ones that we've seen more than once. And the ones that have heavily weighted value are the most valuable to us. It's almost like we're mining gold from these files that we're feeding into the system. We're getting those features or the code blocks that are the clearest indicators as to whether something is malicious or clean. And that gives us that weighting confidence, and it results in that very, very high degree of confidence in the result. So over time, the system becomes more and more accurate, and it also gets faster. You can add nodes to the system, but don't forget, every time you add a node into the system, you have to add connectors, not only from the prior to it, but it to every node in the subsequent layer. And so there's this mathematical complexity. Every time you add a node, you're exponentially increasing the mathematical operation that occurs within the system. But basically, this is the mechanics of AI and how it works. You can take this same system and apply it to other problems. Here we talked about malware and clean files, trying to differentiate between the two of them. You can have AI systems that have hundreds of layers, each with their own respective purpose as far as trying to analyze something and come up with an answer. So I hope that today we were able to give you some insight, not only into AI and how it works, but how it can be used in the security world to solve these tough problems we have, and to take these things, the cyber criminal, out of our playbook, or at least make it very, very expensive for them to operate and be able to break into our organizations and steal data. Thank you very much for your time. I appreciate it. I hope to talk to you again soon.